So hopefully everybody can see the presentation screen there. All right, I got some thumbs up. Excellent. All right, so yeah, I mean, I guess my talk basically is just perhaps even like a little bit of a hybrid talk between sort of how a processor sort of comes out of reset, starts executing code, and how a tool chain that I've sort of been working on building up kind of plays into that, and how it, I guess, would generate the right kind of binary information to allow the CPU to actually start executing and doing its thing. So yeah, what I kind of want to do in this talk is just start off by giving a demo, and then basically explaining like what happened, how it happened, and when, and then probably give a really bad explanation of Makefiles, and hopefully demystify linker scripts a little bit, because they're quite important, and sort of, I guess, in a way where a lot of the magic happens. And I kind of want to show that it's kind of easy as well. Like once you've actually got a tool chain that kind of you can just install and use, that you don't have to be stuck writing assembly for some of these older systems and stuff like that. So a couple of disclaimers. I'm not a software engineer in any way, so linker scripts, Makefiles, all that sort of stuff, they're not my forte. I've kind of figured out a lot of things and got them working, but along the way, and when I'm explaining things, I may get some things wrong, and probably very likely that I'll get some things wrong. So if anybody kind of knows the correct sort of terms or how to do something more properly, then I'd definitely love to hear about it. So yeah, so really, without much further ado, I just want to sort of jump into the demo. And actually, I'm just going to stop screen sharing for 1 second, because I just kind of want to hold up. This is the little board that I'm going to be running the demo on. It's just a little 68K board that I've been working. It's about the size of a piece of A5 paper, and I've just got it hooked up via this serial cable to my computer, which I'm going to use to upload some code using a little serial sort of bootloader. I've got my screen sharing back. So yeah, so I kind of have to be a little bit, we kind of have to fudge things a little bit, because I'm sort of talking about the processor in terms of how it resets, but in the case of this sort of demo, I'm sort of uploading code and then telling the processor to start executing from an address, but the process would be sort of essentially the same when the processor is kind of running everything. So what I have here is a very simple, like quite literal hello world sort of application. Oh, hang on a minute. Can people see my screen, or is it paused? I might have to hit review. Oh, I see what's happening. 1 second. I might actually need to share a desktop rather than a window. All right. Can everybody see my code editor now?
Yep.
Yeah, okay, cool. So yeah, so what I have here is a very simple hello world application. Basically, we have a main function, and it just printfs hello world, and then it sits in a busy loop, because usually in an embedded application, you can't really return from main because there's not really anywhere to return to. There's usually no underlying operating system that would kind of handle an application exiting out. So we just, busy loop at the end there. And obviously, like, printf doesn't just work like magic. There's got to be some way for printf to kind of output a character and send it via some kind of device, either to a screen or in this case a serial port. So I have this little sort of support function up here called putchar, and that's called by printf every time it wants to output a character. So that's kind of like just that. So with my toolchain, I've tried to make things as easy as possible to use it. So to build this, once you've got all of your sort of include files and stuff set up, and we kind of go into this a little bit later, but all you really need to do is just type make all. It will run through and it will compile the code, and it will produce a binary image out the other end of it. Basically, it will extract the code, but I'll get into that sort of stuff later. So we compile the code, and then the next thing I need to do is I need to upload it to my little development board. So I run this script here, which will upload it to, you can't really see that very well, but it will upload it essentially to address 0. And then I'm going to tell my little monitor sort of bootloader application, or to basically start executing from address 400, which is essentially what the CPU would have done with this if this code was programmed into ROMs. So when I run this, what I expect to see is hello world to come back, and we hope that it will. And yes, indeed we do. So this text here is basically come back from the board over the serial connection from the that I've got running. So that's the very quick demo, and like what just happened, because like a lot of stuff has just kind of happened there. It's I've kind of whizzed through it maybe a little bit as well. We've sort of done, we've compiled some code, we've executed it, and a lot of stuff is going on in the background to even produce a sort of binary image that can be executed. So what I'll do is I'll kind of go into some details now about sort of what has actually just happened. And I suppose the first thing to talk about is the reset procedure of the CPU. And as I said before, we kind of need to just like turn a blind eye to the fact that this didn't actually, execute straight out of a reset, but there's kind of two ways that like a CPU would sort of start executing code. And like the two ways that I know of really is that on reset, the program counter gets, initialized to some sort of default value, and then the processor would start looking at that address for the first instruction that it wants to execute. So for example, a Z80 would reset the program counter to 0, and at address 0, it would expect to find the first instruction that it can start executing. On other CPUs like 6502 and the Motorola 68000, it kind of, out of reset, it will kind of look towards an address to find, I guess you might even call it a pointer to another address where the first instruction exists. So 6502 is kind of like somewhere right up the top of the address space, like FFFC or something like that. For a 68K, it's at address 0. And at address 0, it sort of expects to find two values, one being the supervisor stack pointer and the initial program counter. So that initial program counter value, which is kind of the second value, which is from address 4, gets loaded into the program counter, and then the CPU starts looking from that address for the first instruction to start executing. So that's kind of how, that's kind of, I guess, what I've sort of imitated with my little bootloader script. I've sort of told it that, the first instruction will be at address 400 hex. So I've kind of, in a way, just sort of emulated the CPU coming out of reset, but obviously it was not necessarily running out of reset. So what I want to talk about next is, because this is kind of, I guess, the first thing that you would have seen me do is sort of run make to compile the code into, we kind of almost always think of like compiling the code as sort of taking the source code and turning it into a, an executable. It's a little bit more complicated than that, but yeah, it's sort of the first thing you might do is, perhaps type make at the command line to sort of compile all of your code. So we'll have a look at the Makefile that I've got set up for my little project. And really, it's kind of a little bit like a script. You can just use it to sort of set up rules. In those rules, you can kind of execute other applications and get them to do things with, files. You can pass files into a compiler. You can pass files through other scripts that you've written. Yeah, so you can just build up rules to do all sorts of different things. You can also use, variables and stuff to specify, flags that you'll pass to these other scripts and applications, like optimization levels, paths to include files and libraries. And yeah, you can I guess you can also sort of set up your rules to do, other things for you, like the utilities. So cleaning up temporary files, that result from the compilation process, and very specifically in this case, like extracting a binary or like a ROM image from the executable. So I'm going to jump over here back to my editor and just sort of open up my Makefile and give a bit of a tour through, what I've sort of come up with, sorry. So the first thing that I have in my Makefile is basically just a list of all of the object files that are going to be created as a result of compiling the source code files. So each of the object files listed here corresponds with another like source file. So main.o is going to correspond with main.c. Hardware init hook.o is going to correspond with hardware init hook.c. You just specify all of the different object files that you're going to need to create as part of the compile process. And GCC has sort of an ability to work with a lot of different like Motorola CPUs. So I have another little variable here where you can specify the CPU type. And on my board, I've got just a regular 68,000. So I'm specifying 68,000 here as the CPU. I have also used this tool to generate code for the 68030 and the 68360, which is sort of, I guess, included as part of the CPU 32 architecture. The 030 and the 68360 are part of my Cisco reverse engineering sort of adventures. The prefix here is kind of like the sort of very beginning part of the sort of the name of all the binaries for the different GCC utilities. So that kind of just gets concatenated with things like -GCC for the compiler, -LD for the linker, things like that. I have a list of flags here which will be supplied to the compiler, and this is specifying things like the type of CPU that we're compiling for, links to some include directories, and in particular -O for optimization, which can help a lot with sort of code density and also a bit of speed. Linker flags specifies the linker script that will be used during the linking process, and also a link to, well, specifies where it can find a library. In this case, it's called libmetal, which is basically something that I've just come up with. It's kind of like a libc, includes a lot of your sort of standard functions like memcopy, memset, string copy, that sort of thing. Printf, for example, which the printf that I'm using is kind of it's a bit of a fork from one I think that was supplied by Embedded Artistry, or was that a reference to something else? But yeah, it's sort of an open source, very minimal, sort of lightweight printf designed for embedded environments. Yeah, and then we sort of start getting into all of the rules that start to make everything happen. These first few rules here are kind of sort of, I'm not 100% sure the best way to sort of describe it, but it's sort of, for any given input object file, and with a corresponding .c file, we would sort of pass that through to, the C compiler with these flags. And the same thing for like any object file and a corresponding .s file. .s in GCC sort of world is kind of like an assembly file. But the difference between .s and like capital and lowercase is .s, you can run through a preprocessor first, so you can do like defines, if defs, and all that sort of thing, whereas lowercase .s, you can't pass through a preprocessor. But yeah, that's just basically essentially passing them through the compiler as well. BM binary is the output file name that the compilation process and linking process produces. And that is actually an ELF format file. So we're not quite at the end of it, in terms of getting a ROM image yet, but what this basically does is it says like, it's essentially saying create a file called BM binary, and all of the input will be, or the input files will be the object files that were listed up the top here. So all of those object files will get passed into, in this case, the linker, which will then kind of glue everything together and resolve all the, function and variable references and that sort of thing. And then here we sort of have where I kind of get into, like, I guess the, sort of little custom helper, sort of rules that I've created. So all was the one that you saw me run earlier on. So make all would basically run the BM binary rule to sort of, I guess, compile everything and link it together. And then also run this rule called ROM. And if we skip down to sort of the ROM rule, this is where we can kind of see what I'm using here is a utility called obj_copy. And I'm sort of feeding in BM binary, which is the ELF file that was created out of the compilation process. And I'm extracting out the binary contents and putting that into bmbinary.rom. And that there becomes a ROM image that you can literally take, program it into some EEPROMs, pop it on the board, and that will be hopefully executing code when the CPU resets. John, to answer your sort of question, yes, we can do srec files. So I've actually had this in pretty much from the beginning of my toolchain, but we can use obj_copy to take sort of the binary contents out of the ELF file in srecord format as well. So that could potentially be used to feed into making CPM binaries. And as I was saying before, you can kind of use Makefiles to kind of run other little custom scripts and all that sort of thing. So I also have this little Python script, roms.py, and basically what that does is it takes this bmbinary.rom file and kind of splits it, odd bytes and even bytes into two separate files. And then those kind of become the two ROMs that you would program in, a typical sort of Motorola system. Yeah, and there's other couple of rules, like for example, clean is just going to remove all the intermediate files. So object files that get created as part of compilation, and dependency files, which are something, like to do with, includes and that sort of thing. GCC will kind of find out what include files does a source file use, and it kind of builds a dependency list of dependencies for each file. So this just sort of cleans things up a little bit. CRT is the C runtime file. We'll get into that a little bit later on. And then things like dump and dump_s and hex dump, these just kind of allow you to sort of dump the contents of the ROM files, just without having to remember how to type everything in. The difference between dump and dump_s is that both of them will kind of dump out a disassembly of the binary or the ROM image. Dump_s will dump it out with all of your sort of original source lines. So you can kind of see, like, if I had this statement in C, what did that get compiled into? So there's kind of a bit of a rundown of Makefiles, which I hope sort of everybody managed to get something out of. The linker script is kind of where I think a lot of the magic really starts to happen. And the linker script is kind of, or the linker, I guess, as I think I might have hinted before, is kind of responsible for sort of gluing everything together. So the compilation process is kind of like take a source file and produce like well, I think they call it object code, but it's basically like, here's a list of all the instructions that the CPU would have to execute to run the source that you sort of typed out. Inside there, you could have function calls, you could have references to variables and things like that. The compiler doesn't really know where all of these functions and variables are, even though it's the one sort of producing the code for them. But the linker is sort of more so responsible for not only taking all of the object files and gluing them together, but then resolving all of those references. So a function call from one file to another file, the linker will kind of find out what's the address where this function exists in memory, and then go and place it back in the other file so that, that other file basically can, actually execute a call to that other function. And I guess the way that it does that is using the linker script. It will then know sort of what sort of memories are available on the system, where they are, how big they are, and what should go into those memories. So whether it's going to be sort of program code or read-only data like strings, data like variables and stuff like that. So jumping back over to the editor, and if I bring up my linker script, how do I, this is kind of in the way. Drag that down here. So quickly back to the Makefile, we can sort of see here the L flags variable has a reference to this file called platform.ld. And that's sort of the linker script that's going to be passed to the linker during the linking process. And then platform.ld here is kind of the content, or that actual file. And what we have in the linker script is, well, what I've sort of done is I've tried to make it simple, so that I could understand it in a way. And so what I've done at the top here is just a couple of variables that allow you to specify for your ROM, the lowest address in the ROM and how big the ROM is. And then again for the RAM, the lowest address of the RAM and how big the RAM is. So, that's sort of how you kind of, well, this is kind of the beginnings, I guess, of how you tell the linker, like, where is my ROM? Where is my RAM? How big are they? And then when the linker places things into those memories, it will know, where in those, well, what addresses, to resolve, function names and variable names into. Stack size is kind of just, it's sort of a number in a way that just sort of allows me to reserve a bit of space at the very top of RAM to be used as the stack. And I'll try and get into that a little bit further on, how that kind of plays into things. What else have we got? So a startup file is kind of just telling the linker, like, where is the file that contains the very first piece of code that is going to run when this application or binary would start executing. The output architecture, M68K, seems to work fine. That doesn't seem to really need to change, from one processor to the next. Like in the Makefile, you might have to change what sort of processor you're building for, but it doesn't really seem to matter too much in the linker, on the linker side of things. Here I just have a few more variables that I'm calculating some values, just sort of starts and sizes and that sort of thing. A little bit of fiddling of the stack size just to make sure it's always a multiple of 16 bytes. And here is where we start to define all the different sort of types and memories and actually start telling the linker, some of the information that it needs. So here we're kind of defining 3 different types of memory. And well, actually in actuality, the first 2 are kind of part of the same physical memory. So EVT is a memory which basically is the exception vector table. So this is where all of your things like the like initial stack pointer and program counter values are going to go, and also things like all of the vectors for the different types of exceptions and interrupt handlers and that sort of thing. Text is sort of typically what would be, text is kind of like all of your program code. I'm not 100% sure where the name comes from, but yeah, text is where you would usually find all of your like program code, and data is kind of the like the RAM. So this is where all things like variables and and whatnot are going to go. So really these first two here are kind of synonymous with your ROM, and this one here is synonymous with RAM. And then we start getting into defining like what's actually going into these different types of memories. So we now start to define some sections, and the sections are what kind of says, yeah, this is going to go into a particular memory. And there's a particular way you do this. It's not 100% immediately obvious, but bear with me for a second. So the first thing I'm doing is I'm creating a section called .evt, and although it's got the same name here as this memory, that's not really any relation at all. So I created a section called .evt, and then the first two things that I'm placing into EVT are the value of the initial stack pointer and what will be, I guess, loaded into the program counter when the CPU resets, and that is going to be the address of a function called _start. And I'll get into a little bit later where that actually lives and how that comes together. The next thing that we're placing into the EVT are basically all of the vectors for the different types of exceptions that the Motorola 68K can kind of handle. So bus errors, uninitialized interrupts, all your different IRQ sort of vectors, traps, stuff like that. And down the bottom here is a little bit of space, or a little bit of information that sort of tells you how to sort of calculate, like if you're doing, say, if you're doing sort of non-vectored interrupts on a Motorola 68K, you would typically be using these sort of IRQ vectors here. So anything that's auto-vectored, you don't really have a choice about maybe branching directly to some specific ISR. You would branch into one sort of handler for that IRQ level. And then in that IRQ handle, the ISR, you need to kind of go and test all the different potential peripherals that can generate an interrupt at that level and figure out which one has actually done it. So yeah, so that's sort of your sort of auto-vectored IRQ handles there, but then you can also sort of define if your peripherals are smart enough to be able to supply a vector when they generate an interrupt, then this sort of information here is just kind of telling you how to calculate the address for where that should be placed inside the EVT. And so as I was saying before, this section name here doesn't really have any reference to the memory name, but at the end of the section, you have this sort of, greater than EVT, and this is kind of where you're telling the linker which section to place all of this data into. So it's at this point here that I'm saying, take all of this, all of these values here, and place them into the EVT section. And through this sort of memory block up here, these definitions, I can sort of tell, where exactly, like a physical address, that information should be placed. So _EVT org is basically considered to be the same as ROM base. And in this case, ROM base is address 0. So my exception vector table is going to address 0, which is where the 68,000 starts, that's where it loads its first couple of values from out of reset. And all of this sort of business in here is basically just choosing the correct value to place into the EVT. So what we're doing here is we're kind of looking for a function to be defined called bus error. And if it is defined, then what it's going to do is it's going to place the address of that bus error function into that position in the EVT. Otherwise, I'm just going to place the value of a default interrupt handler, which doesn't really do much at all. So this is kind of how you sort of, can define, individual functions to handle all these different kinds of exceptions. You basically just need to create a function with the correct name as per the linker script, which obviously you can change if you really wanted to. But then that would sort of, allow you to create or an exception handler or ISR for any of these sort of predefined ones, or any of your sort of user-defined vectors. Yeah, so next bit then, I guess, is this sort of section here called .text, and this is kind of where all of the program code that gets generated, so all the instructions, they're all going to be placed into the .text section. That's kind of handled by this rule here. So this is just kind of going to capture, like, any time the compiler emits something into the .text or .text .something section, then the linker will find all of these, gather them all together, and place them into the .text section. And then the .text section is going to be placed into the text memory. So our main function, our little support function for printf, any other code that has been compiled, that's all going to end up going into the ROM. And then we have RO data, and this is going to be all of your things, like, so if you have any strings, I guess any const data maybe, that will go into the RO data section. And then this is where things get a little bit interesting. Let me see if I can sort of explain this. The RO data section is going to go into the text memory as well. So all of your read-only data is going to get placed into like the ROM. And I'm sort of telling it that I want to load it at the end of the .text section up here. So I have this kind of like intermediate variable, I suppose, where I've sort of captured the end, like the end address of all the program data, instructions and whatnot. And then I'm going to feed that into this sort of RO data section and say, place RO data in text after the text section, .text section, basically. I hope that makes sense. And then we further have another sort of section here, .data. So this is where all of your like static variables are going to go. Something that only really became apparent to me sort of like in recent years was that, like, when you define your variables and stuff, a lot of times they just go on the stack. They don't actually go into like a fixed physical memory location. So this was a really eye-opening thing for me. But so anytime you have like a static variable, that will typically be allocated to a physical memory address, because that kind of needs to hang around between function calls and that sort of thing. And it might also potentially have like an initialized value when the CPU or when the application starts running. So any of your sort of static variables, or anything that's not going to just be worked with on the stack during runtime, they'll all go into the .data section. And the syntax is a little bit confusing here, but the .data section is going to be placed into the data memory. But we also have here that we want to like store it at the end of the RO data section. And if remember, the RO data section is going into the ROM. So this looks a little bit confusing, but basically what this is saying is that when you have static variables with initialized values, those initial values kind of need to be stored somewhere so that when the application starts up, it can load those values into those variables. So we're kind of telling the linker, allocate a position in the RAM where that variable is going to live, but then store the initial value for it in the ROM after the RO data section. So I'll try and show you a disassembly of the ROM as well, and we can kind of get an idea of kind of how this is all fitting together. But I hope that makes sense. It's kind of like, a little bit confusing at first when you see it, but that's basically what's happening. Is we're sort of just telling the linker to allocate the variable in RAM, but store its initial value in the ROM, because obviously the initial value needs to be stored somewhere, and it needs to be initialized. So that's kind of where that's going to get stored. BSS. BSS is another one of those, I guess, probably very legacy kind of names, but BSS is basically the section where uninitialized variables go. So if you have a static variable that you declare, but you don't give it an initial value, it will get allocated in, or you'll get placed into the BSS section, which will be allocated out of RAM, but it doesn't have to worry about storing an initial value anywhere. But usually what you would find, and it could be kind of implementation specific, is that BSS section would just basically be zeroed out at start. So anything that you sort of allocate but don't give a value, and if it's not on the stack, would basically start off with a value of 0. But yeah, it's one of those things that you might want to sort of test if you were using, somebody else's tool chain, just to see, what do they actually do with a value that is like uninitialized. And these final two here are kind of where that stack size variable that I spoke about at the top kind of come into play. So here I said that I was sort of declaring or defining this stack size variable with 4K as a value. And what I'm basically doing is I'm just sort of reserving 4 kilobytes of stack, or 4 kilobytes of RAM at the very top of RAM. And the stack pointer is kind of going to get initialized to the very top of RAM. So there's sort of 4 kilobytes for the stack to work with there. And that 4 kilobytes is kind of taken away from essentially all of the unused or unallocated RAM. So between the end of the BSS section and the start of the stack is the heap. And I believe I've got the terminology for the heap right, but the heap is essentially any RAM that has not been allocated, is not being used by anything else. John's shaking his head. This is what I understand, but yeah, so basically between the end of BSS and in this case, 4 kilobytes from the end of RAM, I have this section called the heap, and things like malloc would allocate, dynamic memory allocations from the heap. So yeah, John's nodding his head there, so I've at least got one thing right. Yeah, so you can kind of see, I guess it's all sort of here in these formulas and equations and stuff, but yeah, this just basically gives, because I guess one thing you wouldn't really want to happen is to do like a bunch of memory allocations, and then all of a sudden you start allocating memory from, what your supervisor stack is trying to work with. You wouldn't really want that. That might, cause you some headaches. So it obviously doesn't, guarantee that something can't allocate memory from that sort of little slice taken away from the stack, but it's one little thing that you can do, I suppose. So yeah, that sort of hopefully gives you a little bit of an understanding of how linker scripts kind of feed into kind of placing things in different or the right locations within ROM and RAM. And it's sort of through these sections here that the linker will know, like, okay, if all of the if all of the code, all the functions and all that have been placed into the text ROM, I know where, well, it's going to know then what the address of all of those functions are once it's arranged them all. Same thing with variables going into RAM, and then it can sort of resolve all of those as yet undefined function calls and variable addresses and stuff, and start filling them in through all of the object files. So that's a lot of talking. I'm just going to have a quick drink. And theory can be a little bit boring sometimes, so I always quite enjoy a bit of practical sort of practical work. But what we can do to kind of hopefully make all of this sort of fit together a bit better is sort of use a tool called objdump to see sort of maybe how all of these things are kind of fitting together in the actual binary. So using this tool, we'll be able to look at all of the different sections that have been defined in the linker script. what's been placed into them. And yeah, well, if you use the right sort of compile time options, then you can also run like particular commands to sort of be able to view like the actual your source code along with what they've been compiled into. So or your source code lines and what they've been compiled to. So going to jump back over to the editor, and I'm just going to use one of the sort of things from the Makefile, which is make dumps. And that's going to basically spit out all of the contents of the binary file that was compiled. And we can kind of see here there's some very C looking lines here with a lot of assembly code, essentially, sort of showing us what all of the code sort of got compiled to. But if I scroll right up to the very top, then we can sort of see we have here a section called EVT. So this is our exception vector table that was generated by the linker script here. And we can kind of see that, well, these 4 digits here at the start are actually the address, and we can kind of see that the EVT has been placed at address 0 in our sort of ROM image. And we have 2 values at the very start of the EVT, which is this one here, 100,000 hex and 400 hex. And these are our initial stack pointer and initial PC variables, or values, I should say. And this value here, actually, I think corresponds with 1 megabyte, because on my little development board here, I have 1 megabyte of RAM. And just because I've been fudging the way this sort of works, just for the demo a little bit, I've kind of defined my ROM to essentially be the first ½ megabyte of RAM on my development board, and then the ROM is kind of taking up the second half. So yeah, basically, if you put 512K and 512K together, you get 1 megabyte, and this value here happens to represent 1 megabyte. So when my CPU was to reboot, it would load this value into the supervisor stack pointer, and that would give me the very first sort of stack location. And then the second value is the address of this function called _start, and that is at address 400. So the next values that you see here, they're all 462, and that's basically just because they're all pointing at this sort of default interrupt function, because I haven't actually defined any exception handlers or interrupt handlers or anything like that. So they're all just sort of resolving to the default, default interrupt handler, which in this case doesn't really do anything except basically halt the processor. So you can kind of maybe get an idea that like something has fired and gone wrong. But yeah, if we sort of take this value 400 here and just scroll down a little bit and find the text section, we see that we have a function called start at address 400. So when and actually rewind a little bit further, when I uploaded the code and executed it using the little serial loader script, I was telling the CPU to start executing from address 400, because that was basically the start of my executable code. So so we can kind of see here that this is basically, I guess, kind of come full circle now, hopefully. That we've sort of compiled our code, we've linked it all together, we've produced the binary image, and indeed the EVT is kind of pointing our initial program counter at sort of our startup code. And the startup code for the linker comes from this file here called crt0.o. And if I have a look over here in my list of files, we have a file called crt0.s, which is sort of the source file for that object file. And this is basically the very first code that the CPU is going to run when it starts executing. And if I scroll down a little bit, these are just some little initialization things that I'm doing, but the real sort of work of the startup code is kind of here. So the first thing we can see that we're doing in our startup code is we're clearing the BSS area. So all of those variables that we declared as static or that were globals that didn't have a value initialized in the code, they're basically going to get zeroed out. So they're all going to start off with a value of 0. So that's how those sort of uninitialized variables are going to get their initial values. And then the second thing that we're going to do here is we're going to copy the data or the values for all of the initialized variables. We're going to copy them out of the ROM and into the RAM, into their respective memory locations, so that all of those variables that we gave initial values to will get their initial values. And this is obviously applying only to variables that are not stack-based, so statics and things like that. And to do this is just basically a very simple loop. We set up our source address, which is going to be at the end of the read-only data section. So we scroll back over here, and we can see at RO data end is where we're placing this .data section. So we're going to source all of our data from there. The place where we're going to put it is at the start of the data memory, or the data start, and that sort of comes from this variable here. And then it will just basically keep looping through until this A1 variable equals the value of A2. So that's just basically achieved here through this little loop. So we just copy from A0 with a post increment to A1 with a post increment, and then we do a very simple compare just to check whether or not the copy sort of destination start is equal to the destination end. So that there is going to initialize all of the global variables with initial values. Couple of other things that I do is I execute a little hardware initialization hook function if it exists, and basically I just sort of if this function exists when you compile the code, then in this location here in the sort of eventual linked together code will have a value in it, and I just basically test if that's non-zero, and if it is, then I execute it. And then we do the same thing for a software initialization hook. These are just two functions I've seen a lot of other C runtime startup files use, so I've just basically decided I'll include the same thing. But yeah, just initial a couple of little initialization procedures, and then jump to main. So if I sort of go back over here to our disassembly, we sort of have here we have this sort of code that is clearing out the BSS section. Here we have the code that is copying or initialized variables. We can see here that executing the hardware init hook function. So we can see that it's loaded a value 494. So we're going to execute that. The software init hook is not defined, so that's loaded a value of 0. So that'll get skipped. And then, jump to main. So apparently our main function is located at address 484. And actually here we can see 462 is the default interrupt handler. So that's kind of what was just filling in the EBT up here, which is just, basically a halt and then a loop. But main is at 484. So if we scroll down a little bit further, we have main here. And first instruction is at address 484. And the first thing that main is doing is calling printf. So this string here is going to be pushed onto the stack. So push onto the stack like a pointer to this string, and then calling 11E8, which is the printf function. So that's kind of got us all the way through now to the main function. So we can actually see, like if I was to scroll down to address 13C0, it's going to be down the bottom somewhere. Let's move this anyway. 13C0, it does actually have our string here, hello world. So that's kind of where, you know, printf is getting a pointer to the string that it's going to print out, and that is stored in ROM at address 13C0. Yeah. So I think that basically covers everything that I was going to talk about. So there's a link here to, I guess, like my GitHub repo where I've got this tool chain that I've made available. There's some instructions there to install it on a variety of different like Linux OSs, and I'm using it on a Mac, so that sort of works well as well. I believe it can be run on Windows using WSL, but I haven't tested it personally. There's a couple of project templates, so there's kind of two ways, I suppose, you could sort of compile some code. One is sort of like an actual standalone sort of, you know, code, I guess you might say, which is what I've been doing here. And as part of the standalone code, it will actually generate the exception vector table, because it's probably going to be the thing that's, you know, going straight into the ROMs and getting executed by the CPU at startup. And the second thing you can do basically is build like what I've just sort of called an application. And that basically, it does almost exactly the same stuff, but it excludes the exception vector table, because if, I guess the idea being that, you know, you might write like you might sort of build an operating system using the standalone sort of project template, which will then include the exception vector table. And then you might have applications that you build that run on top of that operating system. They don't need the exception vector table, so they exclude that, and that's what you could build using that. The little libc thing that I call libmetal is included in the toolchain. There's just one step required basically to build that. And yeah, there's some general instructions there on like how to sort of use it, how to declare, you know, functions that you want to handle exceptions and interrupts properly, because there's a slightly different syntax to do it. And it basically just tells the compiler to insert the correct return instruction at the end of the function, because you need to use like an RTE instead of an RTS, that kind of thing. Yeah, and I think that about covers all of it. So I'll open it up now to questions.
Thanks, Tom. I'm going to stop recording now and have questions.